Hello guys and welcome back to my channel Civil Construction and Tutor, and this is the continuation to the steel structure designing, and basically we are continuing the steel connection design. So in this video we will be designing the column beam connection, and for now we have a built up column and I-beam. You can see this in the extruded view. So this is the built up column and this is the I-beam. So basically there will be a moment connection, shear connection, gusset connection, splice connection, and these all have their own definition. So for moment connection, there will be the transfer of moment from one of the member to the another through that connection. Shear connection has the transfer of shear from one to another member. Similarly, gusset connection, this primarily transfers the axial force but also minor shear and moment. And basically gusset connection, you can find that for the column and the base plate. And similarly we have a splice connection, and that is used for connecting two members, that is for the continuity of the member. And basically the type of connection depends upon the structural design, that is during the consideration of designing whether the moment has been released or not. If the moment has been released, shear connection will be designed, else we have to design for the moment, and that is the main point we have to remember for the design. So for the beam axial force, shear 3 and moment 2 will be very less. So now let us check for the shear connection as well, and for that we have to release the moment. So for now let us check, and considering this as the flange and this is the wave, so we'll release the moment for the beam that will be connected to the wave. As we know, that is moment is carried by the flanges and shear is carried by the wave. So considering the wave of the column, let us release the moment here. So assign frame, and here you have released partial fixity. So for the moment along both direction, minor and major, apply. Let us check. So it is okay for now, the member is not failing. Now let us see the shear force. You can simply find that there will be slight increase in the shear force. So here you can see the moment at the end, it is 0, but we'll have certain shear force. So we have shear force of 40 kilonewton over here. So we'll design a shear connection now. So let me add a new type, and we'll directly use a shear connection from the template. We can use this option. So firstly we'll change this. I'm using the same file, so I have general section by default, that is the built up section that I had designed. So I'll consider directly this. Okay. And this is the fin plate, and for the shear type connection you will have a gap, because this gap allows the slight rotation, and that's how the moment is released, due to the allowance of the rotation for the member. Load, so we have a load of 40 kilonewton, so it is okay, 40 kilonewton in this vertical direction. And the beam is also 250, that is also okay. Thickness of this fin plate 10 mm, okay. Connection bolted, 10 mm gap. So basically we'll have a moment at this face which is equal to the load V, that is shear force, and this distance. Let us consider this distance as A, and with respect to this we can compute the thickness of the shear fin that is required. Let us select the bolt type. So generally we'll use 4.8 grade of M16 or M20. Let us start with M16. and this is the distance. So if you see, if you keep this 50, or even if we keep this as 30, you can see this is the transverse distance between these two bolts. So basically this is the pitch in the transverse direction, and for the pitch of the bolt, and the minimum pitch is equal to 2.5 times of the, that is nominal size of the bolt, and for 16 it will be 40 mm. So the pitch of the bolt should be 40 mm, that is the minimum pitch. So we have to consider this distance, that is the end distance, which is kept, or which should be minimum 1.5 times of the diameter of the bolt. Considering 16 mm bolt, 1.5 times of 1.5 times 16, this comes as 24. So this distance should be 24 mm, and the length of this plate is equal to 250 minus 30 minus 40. So you will get, this is the clearance. So the length of this plate is simply 250 minus 30 minus 40. So if you keep this as 0 and 0, the length will be equal to 250. So 250 minus 30, it gives as 220, minus 40, it will be 180. And considering the transverse gap of 40 mm, so 40, and the remaining will be the end distance. So 180 minus 40, so transverse, that is 40 mm on either side, 40 40, and it is 180, so 100, and we have 50 mm as end distance from the center of the bolt. So that is the end distance. Similarly, shear plane in thread, so we'll consider shear plane in the thread, so that considering shear plane in thread, we are minimizing the shear capacity of the bolt, so we'll be in the safer side. And shear force transfer, we will be considering bearing or shear tension interaction. And the weld here, let us consider this as 10 mm, that is equal to fin plate thickness. So here we can simply keep this thickness as 5 mm. Let's start with 5 mm, keeping this weld as 5 mm. So we'll consider the single fillet only on the front side, and for now we have model type NVYVZ because we are considering shear type connection, and the forces will be in the bolts. So previously it was node, and if you see for the node and the moment, so there is certain moment at the bolt, which is not true because this is a shear type connection and the bolt is not capable of resisting this moment. So to make this moment 0, we have to make this model type as NVYVZ, and the forces should be in the bolt. Now if we see, the moment will be 0 at the bolt location. So this is one of the things that we have to consider while making the shear connection. So now for the bolt, the moment will be 0. So basically the idea of this shear tab connection lies with this gap. So let me go to the wireframe. Here you can see we have a gap of 10 mm. So considering this weld connection and this gap of 10 mm with respect to the column, so let me consider this as a fixed connection in this type, and this particular length is the gap of 10 mm. Let me assume this as A. Okay, and the shear force that is being considered V will act in this particular point. So we'll get a moment at this face which is equal to V into A. So with respect to this moment M, and we have section modulus for plate ZP as B T square by 4. So this is the section modulus. So here B is the thickness of the plate. So let's take this as the plate, and this is B, and this particular thing is T. We have ZP, and we also know moment is equal to ZP times Fy, that is yield strength of the plate or steel. So we have M as V into A, so we know this value is equal to ZP BT square by 4 times Fy, we have 250 for mild steel. So with this equation and assuming T, we can get the value of B. I hope you can understand now about this gap. Now let us calculate. So the capacity utilization of the bolt is 98.1, which is slightly less than the 100 permissible value. So we can increase the size of weld to be in the safer side. So let us use fin plate of size 6 mm and weld of 6 mm. Then